maybe whatever new I'm gonna say maybe will be after the break. But I thought there's some kind of merit to giving a talk which is where the problems. Sometimes I give talks in which there's some problems which are not just unsolved but not even well formulated, and maybe for a change I'll talk about something which is kind of under at least it's what I'm going to say right now is been understood for a long time. What hasn't been really understood to the best of my knowledge is generalization beyond the flag variety, but we'll get to that. So what's a flag variety? So with flag variety, we only will talk about the GLN flag variety. So GLN mod B. That's this quotient you take. So it can be written as a quiver variety. So this is like a one-dimensional subspace, maybe to the two-dimensional subspace, three-dimensional subspace, so for n minus one-dimensional subspace, and this now maps to n-dimensional thing, and then this is a GIT quotient where the stability means injective. All these maps injective, and modulo the product of GL vi, and that's the resulting action of GLN, which is GLN WN. That's that's by just X and this space. So what's this my thing I very, very often repeat, and we'll repeat it again, is that this is what's flag varieties exist for any reductive group, but what is special for GLN, this is a GIT quotient of an affine variety by reductive group. No such presentation known to me for any other type, and that makes the theory, and you can see that there's a difference between the theory for there's certain differences between what you do for flag varieties of type A and other flag varieties in the way that the ones which in flag varieties of flag varieties, well, we'll get there. Right? And so one easy corollary of that is that if I want to write the tangent bundle, so maybe my X, I want to write the tangent bundle of X. So this is just really the tangent bundle. So this is, maybe I was writing it too big, but it's what? It's direct sum. Maybe you write over all dots in this quiver, you take, or all arrows in that quiver, take the home from the corresponding. And then when you mod out, by direct sum of overall dots, home from the dot itself. Just by construction. This is what's written here, is that all maps here, and you just mod out by it. This is the Lie algebra of this group. Okay. So now if you have any curve C, then you can study, first of all, of course, you can study, it doesn't have to be a curve for now, but let's say, we're going to be talking about curves, so let's do curves. So I want actual maps here, well, you can just say, what's it going to be? You're going to be, you're going to just pull back that diagram. It says, this is going to pull back for me. It's a bunch of each one of this each one of this will be some bundle over my curve. V, and there'll be humps between all these bundles. And that's, but and this maps between bundles will be well, maybe first I'll just define Quasimaps, and then will be easier to explain what's the difference. So these are points of X in torsion free or in vector bundles. See, so this means I have a collection, i.e. I have a collection of vector bundles, E1 of rank 1 going to V2, Vn minus 1 over n. Where these maps are, for me now, they would be that this is, so they're so these are this map, so this is what's the technical word to say? So this is I allow a typical thing I allow is the inclusion if so for instance if I take so this corresponds bundle of different rank, but I'll give an example with bundles of the same rank. So if I take a structure shift of my curve C and I look at those that vanish at some point P, then this is included in OC. So it's just the sections that this is a line bundle, this is a line bundle, this is a map. And this kind of, this map is injective, and this kind of maps are allowed in this diagram. It's usually when we talk about maps to the flag variety, the actual map to the flag variety would require all the quotients to be torsion free. In fact, here the quotient has torsion. So this sort of thing is allowed. And this is by virtue that you allow this kind of, you can call it singularity, means if any of this quotient has torsion, maybe you call it like a base locus of this map. By allowing this kind of singularity, this space achieves a certain compactness. That is a proper space. This is. And it has, moreover, it has a virtual tangent bundle, which is, just given by the exact same formula as before. You take here instead of so where you previously had homes, now you have a sheaf on a curve, So there's of course a space of homomorphism from that sheaf to sheaf, but since on the curve there is a higher there's the x1. So you have to put all the x this kind of whole of this x into this x. And so this means what? This means in principle, this can have, so this is how am I supposed to read it? So there's the deformation space which has to do with home from a bundle to a bundle. And in principle can have abstraction, has to do x1 through bundle to a bundle. Here, there's auto x0 is since I mod out, this is x0, so this is x0. This is the Lie algebra of the automorphisms. And x1, these are just deformations of my bundles. Yeah. Right? So this is the way that this is. I subtract the automorphism, I add back x1, which is the deformation. So this has a, so this is sits in the, you mod out by the automorphism, the actual deformations are homes here and x1 here, and there's abstraction come from x1. Sure. So you can write it as an actual complex, but I'm interested in the K-theory class right now. So okay. So this kind of there's a bit of a miracle. Is that this fact smooth? For x equals p1, and in fact, if it's smooth, even the map. So if I take the Quasimaps and I evaluate at a point, evaluate at infinity to the flag varieties x, even that map is smooth. So even if you're take a Quasimap from P1 and then even we can fix some evaluate it at some point. That's it. That's so. But in general, this is a general thing. Okay. So now, we will take. For CP1, yeah. Yeah, I don't know for which other. So this is something like this you can phrase for any quiver, and then I don't know for which quivers for P1 it's smooth. I don't know. It's a good, maybe good question. Maybe not. So okay. So then if we study, in fact, we will study the fibers of that. So we'll study Quasimaps, particular P1 to X, and we will assume it to be non-singular at infinity. That is to say, infinity is not a base point. That is to say, at infinity, there's no torsion in any of this. So the co-kernel of any of this map has no torsion at infinity. And so this is smooth and has an evaluation point. And in fact, I will, since I assume it's non-singular at infinity, there's a, in fact, evaluation map. So I fix it to be in a fixed value at infinity. So this is this is a, like I said, a smooth space. And right. So this is sorry, I forgot. There's a degree of degree of the Quasimap, degree of this Quasimap f. This is so. This is maybe minus degree of 1 minus degree. And so this, of course, topological invariance, and this is space is just disjoint union over all these degrees. And so what goes back to Finkenberg and Kuznetsov. So they back in, I don't know, back a long time ago, back in previous century. So I don't know, 30 plus years ago. They noticed, and now of course this is now, I mean, by the same Finkelberg, it's now viewed as, instance of this Coulomb branch acting on Quasimaps and stuff. So, but this is here. There's an action of GLN acts, maybe acts on the homology. So when I write Quasimaps, I just mean this space. And the quantum GLN acts on K theory space. And like I said, this of course is now extremely special case of the fact that if I study Coulomb branch, then it acts on Quasimaps to like half of the half of. So this is, and so how's this constructed? So this is one way to construct is that one can look at the locus where I have so maybe I have one of this Quasimaps, and I'll denote maybe V dot. And I'd like to have a sub representation such that there is the dot where this is, so this is torsion free, but now this I'd like to be torsion. And that clear. So I'm looking at pairs of Quasimaps that differ at, they differ at finitely many points, or in fact it's enough to differ at 1 point. Torsion. Maybe we make it say torsion, maybe supported. That's a nice joke. e.g., for instance. Jake and Tix. But you whether you make this assumption, doesn't make assumption, doesn't really make it. So you're looking at locus of Quasimaps that differ. It's just it's now called some kind of whole algebra, whatever. So you look at so you have one of this collection of maps, have another collection of maps, and they differ at finitely many points of thing. And I claim that this object here, this has natural virtual fundamental class or virtual structure sheaf. So this is so this is maybe a little bit I don't know, just maybe a little bit unexpected because this is having, if you already have abstraction theory that is kind of, well, there's automorphism, there's deformation, there are abstractions. Then if you add the condition that something is included in something, generally speaking, it's going to be, your abstraction theory will be one step long. Because it's like saying, I mean, inclusion, like an inclusion, it's like having, the map of inclusion is like having one more variable that acts by that inclusion. It squares to 0, but acts by that inclusion. So you have, kind of one more direction. You think about kind of sheaves on some space, it's like you have one more direction in one more dimension. So generally, I don't know, maybe it's slightly unexpected. But here, even if you're looking for at one step, so if I'll just maybe let's look at one step first. Looking at this kind of thing. Or so you can look at either. So you can look at either. So maybe call it I. That I place. So you can. So this is, you can deform, the first arrow or the second arrow. And so if we deform the second arrow, deformation. So these two arrows, they each of them determines the other. So deform one, deform the other. So might as well deform the second arrow. Deformation of a map, vi going to delta vi. So in principle, so there's, of course, there's home, vi to delta vi. But there could be an abstraction comes from x1 of vi to delta vi. No, just deformation of the map. Yeah, because if you deform all this too, this is so if you're that's right. So if you're the point is that this is torsion free and this is torsion. So this thing is, there's no such thing. Because by duality, that will be a home from something torsion to something torsion free, and there's no such homes. And similarly, when you're trying to deform this kind of map to some source, some other thing. So what's your, when you deform the diagram, what's the abstraction? The abstraction is that you have, this map has to commute, right? So if you deform all the arrows in this diagram, then you get the commutator here. So the abstraction here, the abstraction space, if you deform all these arrows, there's abstraction space which has to do with the home from this, I erase this from V0. And you think that could be abstraction to abstraction, there could be x1, but by the argument, we just, so this thing is not here, so there's no abstraction to abstraction. And so this this locus has so the locus of this inclusion has, if I look at the, so I have it the locus of these inclusions. So maybe I do it over the Quasimaps. Just forget the maps. Get the Quasimaps. And so if I compare compare the virtual tangent space here with the virtual tangent space here, so I can make the relative virtual tangent space. That in fact is something very, very simple. So if I take, it's just this, so we keep writing, so maybe I'll write it here. So we keep writing this sort of expression. First we have, maybe denote by FG, we denote the K-theory pairing. That is to say, we take the Euler characteristic on my curve of F2 tensor G. And so in particular, we're interested in, so for the curve, for this Quasimaps that we're interested in, for the curve being P1, and we fix the value at infinity, this means that I take Fg to be the Euler characteristic on P1 of F2 tensor G, and I will twist it down by minus infinity, because we fix the value at infinity. So that's, and so that having that, then we define, if I have two, like a quiver worth of these things, then I denote this to be, so let me get the sign out again. Look at my notes. This is the sum over all arrows. I take F and G, and then I subtract the sum over all F. So it's kind of like, it's like the formula for the tangent bundle, only polarized. So this is my favorite kind of trick, is that the tangent bundle in the modular shift situation, tangent bundle is always some kind of bilinear expression, and so you can in fact view it as a function of two arguments. So this relative virtual tangent space is just the pairing of what? It's just this dot. So in other words, you here the tangent space. This is V prime V prime. Here it's V V. And the inclusion is just that kind of slightly asymmetric thing. But for flag varieties, this is in fact for flag varieties for x equals GLN. on B again, and C equal P1. And it's kind of a miracle that this thing is in fact is a vector bundle. Vector bundle. And so this is, we decided there's a miracle here that this thing's in fact smooth. That's a vector bundle. So that's just the Euler class of the vector bundle. So this is the, and so this is the fact that the inclusion is just cut out by the Euler class of the vector bundle. But in general, even if it isn't a vector bundle, then still there is a virtual thing, and that's. Yeah. So if I look at the full virtual tangent bundle here, then so maybe with a minus sign. So this is so the virtual tangent bundle here, right? You should think of this. This is like a submanifold, right? So submanifold. If I take the tangent bundle to that submanifold, and I subtract the tangent bundle to the ambient manifold, you should think of this as like being submanifold. So if you think of the tangent bundle to submanifold, you subtract the tangent bundle to the ambient manifold, you get minus the normal bundle. So this is the normal bundle to that. So this says by which equation is it cut? So if it's so for instance this happens to be in fact a vector bundle for projections. It's really cut by the Euler class of vector bundle. And so now what I can do is I can just use this. So this defines me a correspondence, right? I can. Funny that I kept, maybe the first time I spoke about this in Berkeley was almost 20 years ago, and at the time Nakajima and Vasero asked me, what is this for? We were at the time, Badavesh and I were thinking about this kind of thing for Hilbert scheme. So because for Hilbert scheme it's the same. If you're looking for like one thing, so if you're looking for one thing inside another thing, that has that one being a sub-scheme and the other has a virtual structure, and you can use the same kind of thing. So I'm getting old, but the ideas maybe not. So anyhow, so this is okay. So now of course if I just take this correspondence as is, I can read it. I can read it backwards and forwards. So, but this defines me some kind of operator. If I pick, if I go, I can raise, I can lower. But if I pick the ones that change, so this in principle, if I this controls the change in degree. And for instance, the smallest possible change in degree, kind of minimal simple generators, is when this delta V, that's just really 1 point. Just means, so this is in principle, some bunch of sheaves, but they're all 0 except 1 point. Right? And so these are you have this quiver, and at some point you either add a point or remove a point. Those are the simple generators. And the whole, and so this define, if you take this 1 point, so maybe like a delta, I'll write it maybe that, maybe this. So this is delta VI. This would be O of 0 if I equal to K and 0 otherwise. And this defines for me defines for me the operators EI, FI. So this would be raising. Not really. So this would be the kind of the question. Because in general, so this is always, you always act. You can you can replace by T star of X, but you take some kind of critical K theory, critical homology. But that yeah, you can do that. Yeah. But you will not. This will be at some. There is some story about that. Yeah. There's some critical. So if you replace by T star, you need some kind of critical stuff. Okay. Yeah, sure.
So, would you explain a bit more about which deformation? Because in the beginning, I was getting the impression when we talked about deformations of bundles.
Yeah.
We're essentially talking about deformations, metric sets, like kind of also do that in a categorical sense, right? There is a notion of what is a deformation of an object in a category. And so would you highlight to me what we're doing and how you would, for example, know that we end up with this relative virtual extension bundle, right? Whether that also has a deformation theory.
That is deformation theory. That just says what is this somehow? What is this? There's some kind of guy here that's cut out by equations. This tells you what the equation. I mean, the deformation theory is just deformation theory of sheets. Because I mean, bundles with some kind of maps, you can think of like modules or some algebra. This is like, so I'm thinking about, so you can think of whatever, some either deformations of modules over some sheaf of algebra, sheaf of modules over sheaf of algebras, and that sort of thing. Right. So I didn't say anything which is not at least 30 years old. But one kind of cool thing, and that's kind of slightly important, is that if I consider instead.
And Andrei, you get a highest plane module for EF fraction?
Yeah, that's in Verma. It's a Verma, yeah. So this is Finkelberg inclusion. So
it should be related to RA model.
Of course, it's related. Yeah, of course, it's the story we know well. I'm not just saying. I'm just somehow finding common ground here. So instead, if we take all, so it's kind of universal. In other words, kind of universal raising operator. It's kind of really nice. What is it supposed to be? It's some kind of expression in, it's in principle. It's some kind of expression in maybe, kind of, and plus means you raise by whoever, right? So you don't, I'm considering I have some sheaf and I raise it any way I like, right? I mean, it goes to all possible spaces. And this has a very nice, in fact, you can think, it's going to be, if you see an exponent, maybe some kind of completion there. So if you see an exponential here, it's going to be in the group. So in fact, what? Right. So so when I say I'm going to raise degree by minimal amount, then then it's some specific operator, just simple generator. But if I ask, let me raise the degree by every possible amount. So it's going to be some series, right? So it's going to be raised more and more and more and more, right? And so, but inside, so I'm just saying, inside of the completion of this n plus, in fact, sits the group n plus itself, right? Because you take an exponential, it's going to sit in here. And so this, in fact, this element is in here, it's this one. Just super nice. That I believe is also was known to Kuznetsov and Filker. So maybe call it like a bold-faced G. Yeah, that's right. Because we need it. We will need it in a second. And so in particular, like if for instance, if you're interested in how to write down, so I don't know, for some reason, if you want to know, this is, suppose you teach, I mean, at one point in your lives, you may be teaching a course in representation theory, or else you will have to code like some kind of action of GLN, things like this happen. And so this is, if I take the fixed loci, I have maximal torus A1 for n inside G of n, which is G of W, acting on Quasimaps. If I take the fixed loci, this is fixed loci, this is the same as Gelfand basis. So what does a Gelfand basis look like? So if for general representations of GLN, so maybe you take if I take a representation GLN, maybe it has some highest weight lambda 1, lambda 2, lambda 3, lambda n minus 1, lambda n. And if I restrict it to GL n minus 1, then this will have, from n tuple, I have to go to n minus 1 tuple. And the relation is that I have this one has to be sandwiched between these two, and then this one has to be sandwiched between these two. So for this interlacing thing. And so this is the finite dimensional representation. If you want a Verma module is what? Is when the difference between, so kind of Verma is when lambda 1 minus lambda 2 either very, very large or not integer. So if you imagine, if these are very, 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 very large, then this inequality is not really meaningful. So this is, you just, if if this lambda 1 lambda 2 may be large, then you're you're just interested in this sort of inequality, and this differ by an integer. By non-negative integer of z. What? Yeah. So this is, I'm just saying, how we're supposed to go from a finite dimensional representation to Verma and back. First, I started, when you write a Gelfand-Setlin basis, this is the basis of finite dimensional representation. It's indexed by this kind of interlacing tables. Yeah, by Gelfand-Setlin tables, because basic fact about GLN that the restriction from GLN to GLN minus 1 has no multiplicity. every reducible appears with multiplicity 0 or 1. And in fact, the ones that appear, they're the ones, the interlacing ones. Right? So if I restrict, if I take a representation of GLN, I restrict to smaller one, I record that. I restrict to smaller one, I record that. And finally, I restrict to the trivial group, and then once I record this whole information, I recorded a one-dimensional space. That one-dimensional space, I can choose a basis vector there called, that will be a basis in my space. So the Gelfand set in basis is a basis indexed by tables like so. For each of this, right? And so now I'm saying that if we talk about Vermas, then this is the situation when this inequality is still valid, and in fact this difference has to be non-negative integer. But this inequality is not there because you think that this is, you think it's like it's like the picture we all like. So if you sort of start with so then so this can kind of move by an integer, but if they're not when the difference is not a positive integer, then this never fills the other guy. Or what it is, it will fill, but we'll get there. So this is yeah, I'm being okay. Well, I apologize. Could be a long talk. So now with the violation of this inequality, how am I supposed to map this thing to the fixed points? Well, the fixed points are, what's it going to be? So this is on my sheaves. So this says that my framing sheaf, if I look at how this acts here, it says that my framing sheaf, says my framing sheaf W. Well, it's really direct sum of O's. On each of which this my torus acts with weights A1, A2, A3, A4, and so on, right? Then I look at the next space. Maybe sorry, I'm writing them curly W(n)-1. This has to be this was length n thing. This is going to be one step shorter, and it has to be included in here. So if everything is sorry, there's a fixed loci of this of A and C star Q that scales P1 source. What sort of a subsheaf I can find which is invariant? Well, the only invariant subsheaf is O of minus something. And what that minus something could be? This could be only lambda 1 prime minus lambda 1. Let's put it in here. This is O of lambda 2 prime minus lambda 2. Here. So W it's a trivial bundle with a non-trivial group action. And namely, with respect to my group action, it's going to split into line bundles, each of which my group scales by this. Yeah. What? Lambda is kind of like, so we will compute what this is. So this is, what's the weight of this one? The weight of this one, what's the weight of that space? Well, what's A1? A1 is the weight of the fiber. So this is, well, look, this one, if we compute, what's the weight for this thing? We'll ask ourselves, how is our, so maybe, so in geometric representation theory, how the Cartan elements are, or how the commutative operators are. So commutative operators act, more or less by either degrees of the tautological bundles, or the first term class of tautological bundles, some other characteristic of tautological bundles. So what are the tautological bundles on my space? The tautological bundles on my space, I have all these bundles V, and I can take their fibers somewhere, for instance, over 0, right? So this is, so if I take the equivariant weight, I'll maybe write has equivariant weight, it's fiber, so maybe say fiber over 0. Or 0. So, and maybe I should write, to be specific, I'll write lambda 1 prime minus lambda 1, and then times 0. Times 0. So I look at functions that vanish to a certain order. So fiber over 0 has weight A1 minus this number lambda 1 minus lambda 1 times the weight times what, I don't know, let's say, what do you want to call it? Epsilon. This is the weight where epsilon is an element in the Lie algebra of this C star Q. This is the weight. So this is the weight of T, the tangent line to my source. Right? And so we conclude that lambda is more or less A over epsilon, but I think you have to, specifically, you have to put rho there. Some kind of, have sum of positive roots. Because I didn't tell you how the action of Cartan elements is related to the, so if I want the equivariant first Chern class of this bundle, this is going to be that. But how is Cartan element related to the equivariant first Chern class of a bundle? There is some kind of correction, which makes sense because representation theory has to be symmetric with respect to all permutations of the A's. The representation theory of JLN is only symmetric once you shift by rho. So that's the matching of parameters. And then now what is how am I supposed to write E? So with that formula, how am I supposed to write the action of just it's written there, right there. So this says that if I want to know how the lowering operator acts, by what? So I have this class of fixed point. I pull it back. I hit it with the Euler class of some bundle, and I push it forward. Right. So then if I what am I supposed to do? I take conventionally minus is just for this is conventional. And then you take the Euler class of what? So I'm cutting out by that. So this is I take V and I push. So which one is the and V? So V is the smaller. V prime has bigger degree. So that the raising operator goes from V to V prime. That means over this side an integrate. So I divide by the Euler class of. That is to say, this is minus the Euler class of minus delta V. And similarly, K. class of prime built-in. This means what? This means you write you have a specific collection of bundles. You have a specific form. You compute this form, and then this tells you what the Euler class means. You have all these entries, so the form will have a range of entries. Whatever appears with the plus sign, you put in denominator. Appears with the minus sign, put denominator. There's a formula for it. This is how. If you look at, I know how Gelf and Zetlin wrote that down, but this will be an actual formula. I mean, of course, reproduce Gelf and Zetlin formulas. Then finally, you'll discover that if it is the case that lambda 1 minus lambda 2 is a positive integer, sorry, yeah, if this is a positive integer, and lambda 1 prime tries to get beyond this lambda 2, that thing will vanish, and so you somehow. The formulas are universal. They apply for finite math representations. That makes sense? What does it mean? What does it mean that this is an integer? It means the ratio of two a's is, or the difference of two a's is an epsilon, is a multiple of epsilon. Okay. All right, so now, I spoke for almost an hour already. I haven't said anything yet, but yeah, but on a small break or want to send me?
Yeah, let's do 5 minutes break.
Okay. Let's do a break.